All right, welcome again. This is part two. Um, I'll share. Yeah, I share already. Share the PDF, lecture sheet with you. All right. Now it's very important to design the absorber tower that used in the natural gas dehydration process. And for that, we need to find out the diameter of the column. And you can find it by adopting this equation, which is say d square equal to 5040 open bracket T naught Z or Z Q for the gas, which is the flow rate for the gas over T close the bracket, and then open bracket rho for the gas over the rho of the liquid minus rho of the gas. Close the bracket, open a new bracket, CD over dm, close the bracket. All this term to the power 0.5. Okay, all this term is to the power 0.5. So now let's explain these terms. B is the contactor inside diameter in inches. dm is the drop size in the micron, which usually we use 120 to 150 micron. Okay, so definitely it will be given. T naught is the contactor operating temperature in Rankine. So you cannot use other types of units. So you have to use these mentioned units. Why? Because this equation is designed for these units. All right. So we have we have the flow rate of the gas, design gas flow rate. It's in million standard cubic feet a day, and P is the contactor operating pressure, which is PSI absolute. Okay. So if it's gauge, you have to change it, you have to convert it to absolute, and you already know that now. You are third stage chemical engineer. You know that CD is the drag coefficient, and rho for the gas is the density of the gas, which is in the pound over cubic feet. Okay, and this can use this equation to find out the value of the gas density. You already got the density of the liquid, which is glycol. So the density of glycol in pound in the British unit in pound over cubic feet is equal to 70 pounds over 70 pound over cubic feet. Z is the compressibility factor. It will be given, yeah. Definitely it will be given, and S is the gas specific gravity, and all it will be given. So here we have a unique equation to find out the absorber inside diameter. Okay, so all these terms and now are clear for you. Okay, and always remember to put this term all to the power 0.5 and do not use other type of units. For example, the temperature around, so do not use Celsius, for example. If you go Celsius, then you need to change it. Okay, so this equation is designed for these units. So here also we have other terms that important. It's very important to find out the diameter of the and contribute in the design process. For example, you have L as the glycol circulation rate. As I mentioned earlier, circulation rate of the glycol is very important in the process. Why? It contribute in removing the water vapor from the gas stream, and definitely its units is gallon per hour. We also have W delta W over Wi. So delta this let's say a ratio, they call it circulation ratio. Circulation ratio, and I also will explain these terms. This the circulation rate in the gallon of PEG. For example, if we use ethylene glycol over pound of the water, W sub I is the water content of the inlet gas. So in the problem, will be mentions, or in the given case study, it will says that, for example, the water content in the inlet gas stream, for example, is equal to, for example, 2 pounds of the water over a million standard cubic feet of the gas. And WO is the desired outlet water content. So here you have a natural gas that's loaded with the water vapor, and you want to dry it. You want to remove or reduce the amount of the water vapor. Okay. So on the other side, you've got another gas. They will call it the dry gas. So this dry gas should they call the desired outlet water content in the pounds of the water per million standard cubic feet of the gas. This will be also given. We also have W, delta W, which is WI minus W naught, okay? And we also have we already mentioned that QG is the gas flow rate in the million standard cubic feet a day. So these terms, now, I hope now they are very clear, and we also will explain them again in the given problem, and we will repeat them. So here we have 1, 2, 3, 3 charts. Okay, this chart is very helpful to find out the specific information that requires for the design process. And I'll mention them when I will explain the problem. So here we have a case study. For example, we have the gas flow rate, okay, which is 98 million standard cubic feet at 0.67 gas that's saturated with water at 1000 psi gauge and 100 Fahrenheit. So here we can find very strange units. Why strange? They strange with our equation, because I already mentioned that we have to adapt these equations. All right. So